So I was saying thanks to the organizer for inviting me here. It's a real pleasure to speak today. And I hope you can read the blackboard. If I write too small, maybe Jacob, you cannot. The light, probably. Okay. Okay. Okay, so as Christian was mentioning, I work on the Bose gas since the starting of my PhD, but today I'm looking at a different perspective, and we are gonna try to derive an effective field theory as a limit of an interacting inhomogeneous Bose gas. So this is a joint work with my collaborators in Geneva, Antti Knowles, Alessio Ranallo, and Pedro, Torres, Giesteira. Let me consider a domain over Rd. For now, I keep D, that is 1, 2, or 3. And let me look at the Schrödinger type equation, where we have phi, the derivative phi t x equal to, and here I take an operator h that I is. Sorry. The integral of some interacting potential. Then here I have phi t y square with some initial data t, phi 0. So h is the operator by the Laplacian plus some constant which determines the chemical potential later, plus an external potential U. Okay. Now, if W is there, so we say that we have a non-local interaction, while if W is non-local, if W is a delta function, then we have a local interaction. And now, if I consider the energy functional, they call S of phi. Now, if we have a local interaction, here we have, so this would give rise to what is called a phi for 2 theory, and this would be the setting that I will actually study later. We fix the dimension equal to 2, and so we have a phi for 2, because here we will have just the integral dx by x to the 4, and so W is equal to the delta function. This will be the setting of my result. What is a phi for 2? Just for those of you who are not familiar with it, is a phi for is formally defined as a probability measure associated with the energy functional S over the space of fields phi that goes to lambda over domain to the complex number, and this is the probability measure mu d phi, which is the exponential of S of phi. So here we see that we have the free energy and the interaction as usual. And so the problem, here I forgot the measure, and d phi is it's a formal uniform probability measure because we don't know if this measure exists. So the construction of this type of measure has a long history since the late 60s from Nelson, Simon, Glim-Jaffe, where in the field of constructive quantum field theory, their goal was exactly to construct this kind of measure. This field is also interested in some other areas of mathematical physics, like or mathematics, like stochastic, what is called stochastic quantization, so in stochastic partial differential equation, as well as this mu is a uniform measure under the flow of the nonlinear Schrödinger equation that I brought over there. So in PDE, there is a long history of works by Burgan. So when let me explain how we can construct this measure. When the interaction is not there, so we have only the free energy, the measure can be constructed explicitly. This is the free energy functional. And P is the law of the Gaussian free field. So with covariance h to the minus 1. And G is the green function, y, with kernel 1 in dimension 1, logarithm of x minus 1, and x minus y, dimension equal to. Okay. How do we construct rigorous listing? We can use the spectral decomposition of the operator H. And then we construct our field phi. Taking the sum square root of k. And this obviously depends on x. Yes. Yes. Okay. Yes, this is true. This is the green. This is approximate. Okay. Yeah. No, sorry. This is only on without the swap. Yes. Yes, it's asymptotic. Yes, it's asymptotic. Yes, this is not unequal. This is wrong. This is not unequal. This is asymptotically. Thank you. Sorry. And these. So to come back, these omega k are IID. Are Gaussians, okay, with standard complex Gaussians with density. Okay, the problem, and okay, these phi are almost surely convergent in HS with S smaller than 1 minus. Okay. When the interaction is present instead, the difficulty of constructing this measure increases with the dimension, and in dimension 1, everything is okay, because we can use a Wick theorem, and the potential, the interaction potential is bounded, and so we have actually that W in L2 with respect to the probability measure P. The problem starts with the dimension greater or equal to 2, where we don't have this. This is not true anymore. And so one has to renormalize the interaction using a Wick renormalization. And so one defines another interaction. Is these dots indicates the Wick ordering. And here we have, what is this? Just completeness is the expectation with respect to the Gaussian measure. Okay. And here I'm subtracting two infinite terms, but which makes the job, and this will allow us to prove that this W tilde is actually in L2 with respect to the probability, the Gaussian probability measure, and so one can construct effectively so we have that phi tilde is in L2 P after Wick ordering, and this is sufficient to show that this thing is integrable by the so-called Nelson bounds. What am I going to say? I do like this. Okay, in dimension equal to 3, I didn't explain what are these renormalization things that appear there. One is energy renormalization, the last one, and the one in the middle is a so-called mass renormalization. In dimension equal to 3 is actually more complicated, and the construction of the phi 4-3 theory needs an extra mass renormalization. In dimension greater or equal to 4, instead, is conjecture that the interaction, the theory is trivial, and so you don't see the interaction, but you have only what matters is only the free energy. Okay, but now let me connect this construction of phi field theories with the Bose-Gas. So we have our Hamiltonian, which I will write directly in second quantization. So integral lambda s Okay, here this Hamiltonian depends on parameter nu, which is basically the inverse temperature. You will see why this plays a role, and we can interpret it as a semi-classical parameter. In fact, if one considers the operators, the rescaled operators, square root of nu star of x and the square root of nu x, and then here, instead of w, which is our interaction, I take a w depending on epsilon, which converge to a delta function as epsilon goes to 0. Then I could reinterpret these fields are the corresponding phi and phi bar. And so that's why we think that the right, in some regime, taking nu going to 0, yes, here is nu going to 0, then it would converge to a phi for the theory. So we work in the grand canonical ensemble, and so we have our Gibbs state. This rho depends also on, I think here there is sorry, I forgot to say something else. That here I have to, what I'm considering, here I have some renormalization constant that I'm subtracting, R, and are the this operator R appearing here, sorry. And is the mass and energy renormalization to the Hamiltonian. And D is the partition function. Okay, then we consider as object, as we've seen in many talks, the p-particle density matrices. It's gamma, depending on p and nu. This is just the trace star of 1, star of yp. Okay, this one. Okay, and what we want, our goal, is so how do we link the many-body Hamiltonian to our field theory through the relative partition function. So this is a calligraphic P. Which would converge to the partition function of the field theory as nu goes to 0, and the p-particle density metric, which would converge to the correlation function of the field theory as nu goes to 0. And no, in 2D, no. Okay, no, it's but okay, yes, you need it because I'm calling it mass renormalization, the first term, and the second term is energy renormalization. But in 3 dimensions, you need an extra mass renormalization. So yes, the answer is yes, we need it. Yes. Yes. So this I call this and like this. So we are looking for these two limits, and the correlation function, I just define it briefly, of is the integral with respect to the measure phi. Okay. But late, but okay. So what are the known results? Here in the audience we have actually, yeah, so this is what we are looking for. This is not the theorem yet, I didn't state it. So I will arrive at least at the statement of the theorem. But these are the two objects that can link the many-body Hamiltonian to the field theory, okay? So we look for the convergence of the partition function and for the convergence of the particle density matrix. Which are the results? We are there are several experts in the audience. So in this direction, in the mean field, so with high density along range interaction, the first result was by Levin, Schnam, and Rougerie in 2015 in dimension 1. Yes. This is no. This is the partition function of the. I didn't define it. Maybe I forgot. Yes, I forgot. It should be over there. Sorry, this is important actually. You understand now? Is the expectation particular or minus v? Sorry. Yeah. Yeah, but this was actually quite important. Sorry. Did I? PF partition function. This is just to label the two. Sorry, the result, the first result was in dimension equal to 1 by Levin-Rougerie. And the convergence is not to a phi for 2 theory, but in the mean field limit, it converges to a non-local interaction. So when we have actually W over there. And then a group of Fröhlich-Knowles-Schlein-Sohinger in 2017, they prove it for dimension equal to 2. Sorry, dimension equal, less or equal than 3, but with a modified Gibbs state. Then there was in 2018 dimension equal to 2, and in 22 the two groups actually prove it for dimension equal to 2, the convergence in the mean field limit for to a non-local interaction. While in 2023, in dimension equal to 2, there was the convergence to phi for 2 theory by Fröhlich-Knowles-Schlein-Sohinger. And then, very recently, by Nam Su, that I think is the talk that Nam is gonna speak about later, they prove in dimension equal to 3 the convergence to a phi for 3 theory. Okay, what we did, Sorry, here it's important to specify that what they did was on the torus, while these results also holds on the whole space, so with an external trap. What we did was to extend this result with a trap. So now let me call W epsilon, which is a short range interaction. Is greater or equal than. So here we have some restriction. Having a restriction on the range of the interaction and taking dimension equal to 2, lambda is R2, so H. And taking U, and here we have some strong, unfortunately strong assumption on the external potential. We cannot allow exponential growth for almost all R2 and theta bigger than 10. I will try to give quickly an explanation of that. Then we have the convergence of the partition function and the density matrices to a pi for 2 theory as so this is our result. So we have the convergence of the two objects over there to a pi for 2 interaction, and for sure we have some restriction on the external potential, which comes from the green function bounds that we have with an external potential. Do I still have 10 minutes? So I just give you, if you have questions, please. Yes. 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 This is actually linked to this theta, and so you need this. Is true, and S is linked to theta is one minus 2 over theta, if I'm not mistaken, and this theta is the bound, the lower bound that we take on u of x, and actually we have some constraint on how the polynomial growth of u has to be. This comes from a Lipth-Thirring inequality that this needs to be satisfied. Yes, to be finite. Actually, you have also an upper bound on S. I think it's d over 2, so 1/2 minus. Because this is d over 2, actually. Yes. Yeah. Minus some constant, actually, because you have a negative regularity. Yes.
So for you,
Yes, basically it's like you're constraining the trapping potential to be on a stripe. Yeah. We try to improve it in several ways, but unfortunately it comes from some bounds on the gradient of the green function for yes, for L infinity lock potential, and we couldn't do better, and I think we cannot. So I just say a few words on the proof. The proof is relies on the proof in this paper. So it's a two-step proof, and basically one has to do first from a quantum to a non-local interaction, and then to a non-local interaction to a local interaction. So we have the W above, no, that I don't recall. This is the local interaction. Then we have two intermediates. And here is the same W that I'm saying there, so it's a short range. Which is equal to another I, and then I would like to define this, but unfortunately I don't have time. It's something that we can prove correlation function converge to minus okay. And this tau epsilon is an object which contains the green function because come from the weak ordering. So first, what we do is to compare the quantum correlation function with the correlation function associated to the potential W epsilon. This is the first step. And then you want to compare gamma W epsilon to the local one. These are P, obviously. So this is the W phi defined above. And to do this step, you actually pass through this V epsilon. So what is different from the torus case is that here you have to deal with the green function of a non-translational invariant system with an external potential, and this complicates the analysis much more. This derivation is done through a technique coming from constructive quantum field theory and large aviation Nelson bounds, in which we have worse convergence, like worse Nelson bounds with respect to the torus case, exactly because of this thing. And from this derivation, we also have this constraint on the external potential. While in this case, the analysis is different, and here what they introduced on the torus case was to bosonic functional integral representation using the Abba-Stratonovich transformation, which maybe is just random names. Anyway, is to link the field theory with the quantum Hamiltonian, And the problem is that, again, here we have a non-translational invariant system, and to deal with this object, we would need to redefine the free probability measure. So we need to complicate the analysis at the level of the free energy. Maybe I will stop here because otherwise it will be, or I don't know. Because otherwise I will have to write a bit more, and I think I will go. Yeah, then I can stop here.